Hi everyone, this presentation covers Chapter 30 on comparative statistics in the third edition of Jacobsen's textbook, Introduction to Health Research Methods, a Practical Guide. In this chapter, you will learn that comparative statistics, such as rate ratios, odds ratios, t-tests, and chi-square tests, are used to compare groups of participants by exposure status, disease status, and other characteristics. Here's an outline of the chapter. Section 31.1 covers comparative analysis by statistical approach. Section 30.2 goes over hypotheses for statistical testing. Section 30.3 goes over rejecting the null hypothesis. Section 30.4 covers interpreting p-values. Section 30.5 goes over measures of association. Section 30.6 goes over interpreting confidence intervals. Section 30.7 goes over selecting an appropriate test. Section 30.8 goes over parametric and non-parametric tests. Section 30.9 goes over comparing a population statistic to a set value. Section 30.10 goes over comparing independent populations. Section 30.11 goes over multivariable comparisons of means. Section 30.12 goes over correlational analysis, and Section 30.13 goes over comparing paired data. So we have a very busy chapter ahead of us. Section 30.1, comparative analysis by approach. So what are comparative statistics? Anytime you do any sort of comparative analysis, you will run tests that compare the characteristics of two or more independent populations, or compare the before and after characteristics of a study population being followed forward in time. Some other terms to be familiar with include parameter, which is a measurable numeric characteristic of a population, and the word statistic, which really is just the measured characteristic of the sample population. That's the result. Inferential statistics are statistics from a random sample of members of a population to make an evidence-based assumption about the value of the parameter in the population as a whole. So whenever you are conducting inferential statistics, you are running statistical tests on a sample of individuals, and you are trying to take that information and infer some sort of truth about the population that you took that sample from. So if you take a sample of students, say from a university, and you give them a survey, what you want to do is you want the results of that survey to be representative of a much larger group of students, because there's no way, if you're on a large campus with say 50,000 people, that you're going to be able to get everybody to fill out a survey. That would probably be a waste of time and resources anyways, but not everybody would participate. So you want what you have from that small group of people to be as representative as possible to the larger student body. So figure 31 goes over analytic plans for comparing groups. And so it breaks these down by the different study approaches or study designs. And then it includes some steps and some key analytic approaches to use for that. So for example, the case control study. In this study, our first step is to show that cases and controls are similar except for disease status. So what you want to do is you want to run some sort of comparisons, and you want to have the results not be statistically significant from each other. And so you can use an odds ratio to see whether cases and controls have different exposure histories. And so you can go over the cohort and experimental study on your own time. So anytime you conduct a statistical test, you will have a hypothesis. And with any hypothesis, there's a null hypothesis and an alternative hypothesis. And so the null hypothesis, which is sometimes presented as H0 or H0, describes the expected result of the statistical test as if there is no difference between the two of the values being considered. So a null result means there's no statistically significant difference between the two. Whereas an alternative hypothesis, usually represented as H with a small a, or it could be represented with a number, describes the expected result if there is a difference between the two or more populations being compared. So a null hypothesis is that there's no difference between the two, and alternative hypothesis would be that there is a difference. And so figure 32 goes over some different examples of hypotheses for statistical tests. So I'll just go over the first one and then you can read the others on your own time. So if the goal is to test whether the average age of cases and controls in a case and control study is different, our statistical question may be, are the mean ages of the cases and controls different? Our null hypothesis would be that the means are not different, whereas the alternative hypothesis is that the means are different. So section 30.3 goes over rejecting the null hypothesis. And so in a study, when you have a statistical result, you either reject the null hypothesis, which concludes that the values are different, and that you reject the claim that the values are not different, or you fail to reject the null hypothesis. And you sometimes see this reported in the literature. And that represents that there is no difference between the two. There's no evidence that the values are different. So if there's, say, a p-value of greater than 0.05 or the confidence interval is not statistically significant, then you have failed to reject your null hypothesis. And when you're calculating those p-values, you're calculating that with something called chance in mind. And chance describes a random event that occurs by happenstance rather than by design. So the decision to reject or fail to reject a null hypothesis is based on the likelihood that the result of a test was due to chance. And so figure 33 has an example of the distribution of mean ages of a sample population drawn from a larger population. And then it sort of discusses how there could be some differences in the means and spreads them out on there. So here we have, so in the middle line here is our mean in the source population. Then this y-axis represents the count, so the number of sample populations drawn from the source population that have a particular mean. And then this shows our extremes, so the sample means that are extremely far from the mean in the source population, which represents 5% of the most extreme sample means. So 2.5% has the lowest means, and 2.5% has the highest values there. And so when we're running this statistical test and when you read the research literature, you will see them report p-values, and the p represents the probability value here. And this describes the likelihood that a test statistic as extreme as or more extreme than one observed value would occur by chance if the null hypothesis were true. So a very small p-value means the observed t-test is highly unlikely to have occurred by chance. So you want the p-value to be smaller because you want to be able to say that it's your study that found the result versus it being due to chance. And so with that, we have a significance level, and we have a significance level set as a cut point of where we either reject or fail to reject our null hypothesis. And what's most commonly used is a 0.05 or a 5%. And so the test result is classified as having statistical significance if the p-value is less than what that measure is, and they'll call that measure the alpha level. And so any statistical test with a result that is less than that p-value or 5% of the most extreme responses expected by chance, which is kind of a mouthful, then when the null hypothesis is true, it will reject the null hypothesis. Figure 34 goes over interpreting p-values, and so here you can see the differences in conclusions. So if you have a null hypothesis of, say, the means are not different, your conclusion when p is less than 0.05 is to reject the null hypothesis, and so that would mean that the means are different. But your conclusion when p is greater than 0.05, you would fail to reject the hypothesis, and that would mean that the means are not different. So most statistical tests use an alternative hypothesis that simply expresses a difference, but they can also say a directional difference. So a one-sided p-value would be used when there is a direction that is specified. So you specify that males have a higher mean than females, versus a two-way or two-sided p-value would mean that there's just a difference. There's not a specified direction. And so figure 35 goes over some differences in the one-sided and two-sided alternative hypotheses. So for example, if the null hypothesis states the means are not different, then your two-sided alternative hypothesis is that the means are different. But then your one-sided alternative hypothesis would be that the mean among cases is higher than the mean among controls. Some of the other ways of presenting measures of association that go beyond looking at p-values and null hypotheses, etc., are the odds ratio and the rate ratio. And odds ratios are used for case control studies, and rate ratios are used for cohort studies. And these are usually presented with 95% confidence intervals instead of with p-values, but they represent the same thing. And so figure 36 goes over some example odds ratios for, say, a case control study. And you can go through and calculate this on your own. I know that there's also some calculations in the chapters on case control study and cohort studies on odds ratios and rate ratios, but here you can sort of see the differences that you can put into a 2x2 table and interpret whether there are differences. So because we use a 95% confidence interval with odds ratio and rate ratios, it's important to determine how you interpret those results. And so I mentioned before that it is similar to a significance level of 0.05. So an odds ratio and a rate ratio, when there's no difference, the odds ratio is a 1.0 or rate ratio is a 1.0. And so a 95% confidence interval that does not overlap 1 is equivalent to a p-value of less than 0.05. So if your confidence interval is 0.80 to 1.2, it crosses that 1. And so that would be greater than 0.05. But if your confidence interval was 1.2 to 1.6, then you would have a p less than 0.05 and your results would be statistically significant. And so here are some interpretations as well. So if our odds ratio is 1.7, but then our confidence interval is 0.6 to 5.3, then there's no association between the exposure and disease. But then our rate ratio below, and they're interpreted very similarly. If it's 1.6 and then you have an odds ratio of 1.1 to 2.4, then we conclude the exposure is associated with the increased risk of disease because the odds ratio confidence interval for the odds ratio does not cross 1. And that's actually very easy to understand if you look at it in this way. All of these odds ratios do not cross 1, And so they're all statistically significant. Now, it's important to also know that a confidence interval doesn't have to be this 95% confidence interval. It can also be set at a 99% confidence interval or a 90, but typically the standard would be 95%. So section 30.7 goes over selecting an appropriate test. So there's a lot of different terms coming up and a lot of different tests that can be used. Sometimes it's good to really come back to this in the future if you do end up doing any statistical analysis, working in academia, or going on to grad school. Jacobsen does a really good job at discussing the different tests. And so whenever you have a test that you want to run on your data, you have to look at the assumptions and make sure that your data meet the assumptions. And you must make sure before running the analysis, because if you use a computer program, they're not going to know what you're running. It's just if you tell it to run a chi-square test, if the data is not appropriate, it's going to run the test anyways, and it will give you inaccurate results. So figure 39 goes over plans for hypothesis testing. And so this is really good to sort of line up the variables you want to compare, specify the goal of the test you want to run, check your variable types because there are different types of tests for different types of variables, choose the appropriate test for the variables, confirm the assumptions, and then run the test and interpret the results. And there are two key differences between types of tests. You can have a parametric test and a non-parametric test. A parametric test assumes the variables being examined have a particular distribution. And these are typically used for ratio and interval variables that have a normal distribution. Whereas a non-parametric test does not make any assumptions about the distribution of responses. And this is used for ranked variables or when the distribution of ratio or interval variables is non-normal. So if you have skewed data or some sort of scale data, you will probably use non-parametric test. Then you may also have some tests to compare a statistic to a set value. So let's say you have a sample and you have the mean prevalence of getting a flu vaccine. And then you have a value for the state of Texas. And the state of Texas says this % of the population gets flu vaccine. So you can take that one mean value and then make the comparison to the state value. And that's a one sample t-test. Or you could have a binomial test, which compares the proportion expressed by binomial value to a selected value, or a chi-square goodness of fit test, which compares the proportion of responses to a nominal variable to a selected variable. And so figure 3010 goes over comparing sample means to other values using the one sample t-test. And so actually the one sample t-test does need to be the continuous data and not something like a binomial variable. But here you can see where the differences can be in the values and the mean. And so section 30.10 goes over comparing independent populations. So not only can you run the statistical tests between one sample and a set value, you can also compare across the populations. And so independent populations are those which no individuals are part of more than one group. And so you can run an independent samples t-test where you take the mean values into two different groups. So if you're looking at the difference in age in two different groups of people, then you would run an independent samples t-test. Then we also have the non-parametric tests. So you have a Mann-Whitney U-test, which is also sometimes called the Wilcoxon rank sum test, which compares median values of an ordinal rank variable to an independent population. And so this would be if you had Likert scale variables, and if you had, say, knowledge of statistics in public health students versus knowledge of statistics in, say, nursing students. They're two independent populations. You could also have the Fisher's exact test, which compares the values of a binomial variable in two small independent populations. And so this is just a much smaller set of values, and it also is a yes-no response. And then you have a chi-square test of independence, which compares the values of a nominal variable in two or more populations. And so this would be if you had, say, that flu vaccine outcome and you compared two or more groups. And so figure 3011 goes over common tests for comparing two or more groups. And so this is a really good table to come back to when you're trying to decide what statistical tests to use for, say, group projects or in the future. And so a little bit more terminology to cover on comparing independent populations. So we have a statistic and we have a test statistic that comes from the analysis. And this is the value calculated from study data for a hypothesis test. And so this could be a t-stat used for the t-test or the f-stat used for a one-way ANOVA. You also have a degree of freedom that is calculated, and this is the number of values in the calculation of a test statistics that are free to vary. And so figure 3012 goes over the examples of tests for comparing subpopulations within a study population. And so again, this is just a good way of looking at how different variables can use different types of statistical analysis. Then figure 3013 has a more simplified version of the previous figure, and it just goes over, say, age, if that's your characteristic, if it's measured continuously, your mean and standard deviation is presented over here as 43.7 among males with standard deviation of 7.8 and 40.1 among females with a standard deviation of 8.1. You can see that females are younger and the variability of data is a little higher, and that our p-value is less than 0.01. Then for current smokers, this is presented as a percentage, which is 12% among males and 10% among females. Our p-value is greater than 0.52, and that means there's no statistically significant difference. Then you can also see here how data can be presented with a frequency and a percentage, and then this is the actual N, so 90 out of the males lived in the north, 50 out of the males lived in the central, and 60 lived in the south, and then it has the percentage. And then you can see the p-value here, there's no difference between the groups. So section 30.11 goes over multivariable comparisons of the means. And so not only can you compare two groups and do two comparisons, you can also do multiple comparisons. So for that, we have the ANOVA, which is an acronym for Analysis of Variance, and this compares mean values of a continuous variable for 3 or more independent populations. Then we have a one-way ANOVA, which compares mean values of one interval or ratio predictor variable across independent groups of people, such as the mean age of patients at 3 different family practices, or it could be 3 different schools is a common one that's used as well. It uses the F-test to determine whether the mean values of an interval or ratio variable are different or not different across 3 or more populations. Then you could also have the Kruskal-Wallis test, and this compares the median values. So this is very similar to an ANOVA, except for the data are not normal. or a two-way ANOVA or a factorial ANOVA, which compares mean values of an interval or ratio variable across groups, and the Levene's test, which demonstrates the homogeneity of the variables across the different groups. And so figure 3014 goes over these different comparisons for you in two or more groups. And then we have the covariance, which measures joint variability between the two random variables, or the ANCOVA, which compares means of a ratio interval variable in two or more independent populations, while controlling for one or more additional ratio interval or nominal variables. So I would say that more often than not, the ANOVA is used, but as you get to more sophisticated analyses, some of these types are used as well. Then we have the MANOVA, which compares differences in group means across multiple dependent variables, or the MANCOVA, which looks at covariance. And this compares the differences in group means across multiple dependent variables, but controls for one or more additional ratio, interval, or nominal variable. Then section 30.12 goes over correlational analysis, and this is when you have two continuous variables. And so a Pearson correlation coefficient examines the association between those two variables. And so it could be that you're looking at, say, age and BMI. So age can be looked at continuously, and then body mass index would be looked at as a continuous number. Or you could have a Spearman's Rho test or a Kendall's tau test, and this is with ordinal rank variables. And so this could be the difference in your scale variables, or if the variables are not normally distributed. Then we also have the phi coefficient, which is a statistical measure of the degree to which changes in the value of one binomial variable predicts changes in the value of another, or the Kramer's V, which quantifies the degree to which changes in the value of one categorical variable predicts the changes in the value of another. And so section 30.13 goes over comparing paired data. So you don't always compare your data to different groups. You may compare it among the same people, but at different points in time. And so variables linked together for the analysis can be gathered before and after, or it could be something where people are very, very similar to each other, like genetic siblings. And so you just do a different type of test where it's a before and after comparison. So for that, we have the match pairs t-test, which compares the values of an interval ratio variable in members of one population measured twice or among individuals matched from two different groups, but they're matched pairs, so they're not, they're, say, the genetic siblings. Or you have the Wilcoxon rank sum test, which is like a pre-post variable test where you have the different scales, or you have a McNemar's test, which compares values of a binomial or nominal variable in one population measured twice, or those matched pairs. Then if you have more than one comparison, you could have the repeated measures ANOVA, and this would be when you look at the outcome at several different points in time among a pre-post test. There's also a Friedman test, which compares the values of an ordinal or ratio variable across several time points or several individually matched populations. Or you have the Cochrane's Q test, which compares the values of frequencies or proportions in three or more matched sets of binomial or nominal variables. And so figure 3015 goes over common tests for comparing matched populations. And so again, this is a really good one to come back to when you have those pre and post comparisons and you want to do it more than once. Then figure 3016 goes over examples of tests for comparing pre and post-test results. And so this has the actual data here where you can see some pre-post differences in weight as the continuous variables and what test would be used for that. So if you're looking at weight pre and post an intervention, you would do a match pairs t-test. Or if you're looking at it as a binomial variable, as the ability to run 1 mile in less than 10 minutes, then you would do a McNemar's test. Okay, so that is it on chapter 30. It was a big one, but there's a lot of information here that you can always come back to in the future if you do any types of statistical analysis. The tables are really good at going through some examples of what you might want to use for your analysis. Thank you for listening.